Let's look at an example of finding t, n, and b for a particular curve. Remember that in order to find t, we want to find a unit tangent. So we know the velocity is tangent to the curve, so we'll find the velocity, but we'll make it a unit vector by dividing it by its length. In other words, we're going to take the derivative of our position function divided by the length of the derivative of the position function. In this case, the derivative of the position function, the derivative of sine t is cosine t, and the derivative of cosine t is minus sine t, and the derivative of 4t is just 4, and the length of that would be the square root of, let's see, this would be 9 cosine squared plus 9 sine squared plus 16. So we have 3 cosine t and negative 3 sine t and 4 over, let's see, 9 cosine squared plus 9 sine squared is 9. 9 plus 16 is 25, and the square root of 25 is 5. So we now have our unit tangent as 3/5 cosine t, negative 3/5 sine t, and 4/5. And you could check this length, the length of this vector is 1, because we took a vector divided by its length. That makes a unit vector. Now our plan for finding n is that if a vector has constant length, its derivative is perpendicular to it. So to find n, we'll take the derivative of the unit tangent. Of course, that may not be a unit vector itself, so we'll have to divide by the length of the derivative of the unit tangent. So we take the derivative of the unit tangent because it's a vector of constant length, and therefore its derivative is perpendicular to it. That gives us a vector perpendicular to the tangent, and then we divide it by its length. So this is also the direction that we're turning in, because if you're changing the tangent, you're going, that's how you're turning, right? You're changing the tangent. Okay, so we'll take the derivative of this vector. Let's see, the derivative of 3/5 cosine t would be negative 3/5 sine t, and then the derivative of sine t is cosine t, so we get negative 3/5 cosine t, and then we get 0, and we need to divide by the length of that. If you square 3/5, you get 9/25 sine squared plus 9/25 cosine squared, and 0 squared is 0, So, so now we have negative 3/5 sine t, negative 3/5 cosine t, and 0, all divided by, let's see, this is, we have 9/25 times sine squared and times cosine squared, so that's just 9/25, and the square root of 9/25 is 3/5. So we just have to divide each of these by 3/5, so we find that our normal vector is negative sine t, because we had negative 3/5 and we divided by 3/5, and negative cosine t, and 0 divided by 3/5 is 0. So finally, we need to find our binormal. Remember, our plan for finding the binormal is to take t cross n in that order, and to do a cross product, remember, we can remember it from our little determinant formula, right? I, j, and k, and then we have t, which is 3/5 cos t, and negative 3/5 sine t, and 4/5, and we're crossing that with n, which is minus sine t, minus cos t, and 0. So let's see what we get. Our I component is going to be 0 minus 4/5 times negative cosine t, so that's 4/5 cosine t. And our j component is going to be negative 4/5 sine t minus 0. So we get negative 4/5 sine t. And finally, our k component is going to be negative 3/5 cosine squared, and then the product this way is 3/5 sine squared, and we're subtracting that, so we have negative 3/5 sine squared t minus 3/5 cosine squared t. Close our vector there. Well, let's see, we have negative 3/5 basically times sine squared and times cosine squared. So so we have 4/5 cosine t, negative 4/5 sine t, and that's negative 3/5. That's supposed to be a fifth, 4/5. Okay, and that finds our binormal. All right, so what we have here is an example of a helix, right? Because without if we ignore the z motion, this would just be the parametrization of a circle, but our z is gradually increasing in time, and so what we see is on this curve, need a little space here, but on this curve, we're going to start out with a circle, but the z will gradually be increasing. So if this is the xy plane, then we're going to start circling around here and climbing as we go. And then we found this function t, which is giving us our unit tangent. Notice that in the z direction we just kind of have a constant increase there. So, and then we're sort of circling around a bit with our unit tangent. So our unit tangent is going to increase with time. And then our unit normal just points straight in on the curve. And it's level, right? There's no z component. And then our binormal is the cross product of those two, which is a vector that points down. See how it has this negative z direction. There's t, and there's n, sorry. And t cross n by the right-hand rule would go down, which we actually see in our B, right? So it's a vector that's pointing not straight down, but it's got definitely an angular component down. So there's our frame. There's a nice tool that's built into Maple that we can use to visualize the TNB frame. It comes with a package that's called the student package, and part of that package is for vector calculus. So first thing I do is I load the vector calculus part of the student package with this with command. Once I do that, one of the commands that's available is this space curve tutor. And this, if you run it, will actually open up an extra window that you can put your function in. So you have your vector valued function. This will open up a window that we can use to do that. We'll just wait a second while that window gets open. Okay, so the window opens up, and we can put in our curve. Remember, our curve was 3 times the sine of t, and 3 times the cosine of t, and 4 times t. So we could run that as far as we like. We didn't really have any particular bounds on t in here, so we can display. Oh, I've got an extra parenthesis here. Okay, so we can display that curve. We run it. It displays our helix. We can look at it. We can even animate it, and it will show us how the TNB frame changes with time as we move along on this curve. So it's showing it. You can see it sort of barely here. Another thing that it does is it gives you the code that you would need to actually run this. So down here, you can highlight this with your mouse. Highlight this with your mouse, and then you can hit Control-C to copy that, and go back here and actually plot it. So you can actually plot so you can do a plot of that TNB frame and look at it and kind of examine it. You can even use the play button here to animate that. See the TNB changing as we go along the curve.